Hello all, I'm back with another video. This one is probably going to be really short. We're going to talk about momentum and later we are going to reintroduce Newton's third law, okay? So this is from, for the international, okay? So for the international, oops, I have to do something about my handwriting. Maybe I should hire someone, I don't know. So this is for the international AS level physics, okay, for from the Edexcel spec, okay, and it's topic 1C in the international curriculum, but I think, and okay, I mean, and this is for unit 1, but I think it's exactly the same momentum concept talked about in paper 1 of the Edexcel UK curriculum. But let me know what you think in the comments. Anyway, so let's dive in. So for year 12 students usually who take the AS level, okay, sometimes there are year 13 students who take the AS level. This is the so-called easy momentum, the linear momentum, okay? So we're going to talk about momentum in one dimension, okay? Those of you who are going to take the international A-level spec, okay, they will do two-dimensional momentum. And those of you who are going to go to university studies, they are going to do three-dimensional momentum, okay? So, but anyway, this is linear momentum, meaning that things move in one dimension, okay? So maybe we have a block of mass m hitting another block of mass capital M that is initially stationary, and then maybe they move together, maybe they stick together like this. So this is the mass m and this is the mass uppercase M, and maybe they move together to the right, okay? So this initial, oops, let's call it U, I mean, because we have the Suvat equations in mind. So maybe U, let's call this M1, and maybe this is U1, and maybe U2 is 0 because stationary, and at the end they move together with some velocity v. Okay, so things move in one dimension. Okay, so with all this being said, let's talk about what momentum actually is. So momentum, okay, is a measure of what will be required for to stop an object from moving, okay? And this means, I mean, you can imagine a car, maybe, okay? Very heavy, it can develop really high speeds, right? So it has a really high momentum, okay? So you can think of a car moving towards something, okay? So if it's a cone in the street, the car will move it over, right? It will run it over because the cone doesn't have enough mass to exert some force on the car and stop it, right? And then you can imagine increasingly putting more and more and more and more and more cones, okay? Eventually, if you build enough cones, maybe the car will stop, okay? Why will the car stop? Because some force is going to be exerted from the cones on the car. So, okay? So the higher the momentum of anything, the more force or mass you need to use to stop it, okay? So this is what momentum is really, okay? A measure of how much force you need to exert to stop an object, something like that, okay? So let's define it mathematically. I think most of you are familiar with P is equal to mv, and we should use vectors, okay? Because momentum and velocity are vector quantities, but here, because you're talking about linear momentum, we will lose the vector sign, But you have to be careful for problems where things move in opposite directions, okay? So you have to use a minus sign for the object that moves in an opposite direction, okay? I think, yeah, that makes sense, right? So what are the units for momentum? Mass is measured in kilograms, velocity is measured in meters per second, so kilograms times meters times seconds to the minus 1. Okay, there is no special name for these units, so we use base units, kilograms times meters per second, to describe momentum, okay? And just for historical context, P is used, so you don't need to know this. I mean, it's not important for whatever problem they are going to ask you in the test. But P is from Latin. We use P to denote momentum because P is from the Latin word impetus, okay? Impetus. That means motion, I think. Motion or movement or something like that, okay? So they stole the P from there, okay? And P is momentum. Okay, so I want you to notice one more thing about units because sometimes I see it in exams. So notice that 1 Newton, right? If you break a Newton down to base units, is Newton is 1 kilogram times meters over seconds squared, right? So I can multiply both sides, okay, with seconds, right? So I multiply the left-hand side with seconds, okay? So I can also multiply. So I must multiply the right-hand side also with seconds, right? So this seconds cancels, okay? And we immediately see that the units for momentum are equivalent to 1 newtons times seconds, okay? So sometimes you will see momentum denoted with newtons times seconds, okay? So this is what I wanted to say. We already mentioned that P is a vector quantity. So, and we also mentioned that at the AS level, we only work with linear momentum, okay? So in one dimension. Okay, let's talk about examples. Let's do some examples to see what momentum I mean, we are going to do some numerical examples to get a feeling of how large momentum can be, okay? So the first example is a bullet, okay, with a mass of 5 grams, okay, and a velocity of 200 meters per second. And shout out to a channel. I mean, I just thought about it, okay, on the fly as I am making this video. There is this guy, if I find the channel, I'm gonna link it in the description of this video. So this guy shoots various guns. I mean, he uses various guns and shoots at targets. And he tries to see how far a bullet can penetrate into material. So bricks, locks, safes, etc. So that's the perfect example of a channel where momentum is discussed, but the guy who makes the videos that is not aware probably that what he's showing are examples of momentum. But it's a fun channel, so I'm gonna link it in the description. So if you have a bullet with a weight of 5 grams that moves with velocity 200 meters per second, then its momentum is simply P equals to mv. So 5, don't forget to convert grams to kilograms. So 5 times 10 to the negative 3 kilograms, right? Times 200. So the momentum is 1 newtons times seconds, okay? And a bullet is a scary thing, but it doesn't look, I mean, the momentum is not really large. Why? Because it's a light object, okay? But okay, because it's tiny, it can penetrate your skin and kill you, okay? But let's go see what the momentum of a car is, okay? Okay, so a car with mass, say 2,000 kilograms, so 2 tons. This is a heavy car. I guess it will be a Jeep or something like that. And velocity 20 meters per second. Not too bad. I mean, not too fast, okay? Then the momentum of this car is going to be 2,000 times 20. It gives us 40,000 newtons times seconds. Okay, so this is a really large momentum. Okay, but to go back, okay, so don't forget these two numbers. Okay, so let me go back to the discussion about a car hitting one cone versus a car hitting maybe 10,000 cones. Okay, the 10,000 cones will probably stop the car. I'm not sure. I'm just making this up on the fly. Okay, and I told you that momentum is a measure of how much force is needed to stop something. Okay, so a bullet can be stopped by a book, right? By a thick book, okay? By a thick book. But the car needs a large concrete wall, maybe, okay? So a large concrete wall to stop. Okay? So this gives you an idea of what momentum tells you, okay? The kind of information it tells you is that how much force I need to stop something, okay? And for the car, you need a really large concrete wall. Hopefully you're not in the car when this happens, okay? And now with the mention of a bullet being stopped by a thick book, I do need to link that channel I was mentioning earlier in the description, okay? So I hope I covered what momentum tells you. I mean, the kind of information. And now let's go see another thing related to momentum. Okay, let's talk about Newton's second law again. So let's talk about Newton's law. Second law. Newton's second law revisited. Okay, so far, I think in my AES level videos, I think we usually use F equals ma, right? To describe momentum. To describe Newton's second law. I'm sorry, I'm thinking ahead. So m times a can also be written as m times dv over dt, right? Because the change in velocity with respect to time is what acceleration is. But now notice that using basic derivative laws, we can write this as d over dt of m times v, because m is a constant, right? Not always, as I will say in a minute. I think I will say that. Do I need to say that? Let me think. I mean, the mass is not a constant in examples like a rocket fired in outer space, right? But for most practical purposes and for the AES level, we will assume that the mass of the object is a constant, okay? In that case, mass can get into the derivative, but now notice that this quantity is momentum, right? So F is also equal to dp, the change in momentum with respect to time, which you can also write as delta p over delta t, okay? So actually, I think when Newton introduced his laws, I think he used this definition, the change in momentum with respect to time, okay? So to write it in words, we can write that the rate of change of momentum okay, is equal to the applied force, right? Let me see, is equal to the applied force and is in the same direction as the force. So this is another definition of Newton's second law, okay? All right, because I mentioned it in passing, I'm gonna elaborate a little bit on something that you don't need to know at this stage in your life, but it's interesting, I think, to know, nevertheless. So remember that we wrote F is dP over dt, right? And this is equal to d of mv over dt. And we can use the product rule of derivatives, right? And write dm over dt times v plus the second term is m dv over dt. I think in all cases you see at the AES level, this term is not used because the mass is considered constant, so dm over dt is 0, okay? But this term is needed when you deal with rockets or any kind of vehicle, I guess, that loses mass as it moves. So jet engines, rockets, that kind of thing, okay? But anyway, at your age, this is enough, okay? So m times dv over dt. All right, now let's move on to a very important application of momentum. And I think most problems at the AES level come from this concept that we are about to talk about right now, and it's the conservation of linear momentum. So let's use the fact that F is equal to the change in momentum with respect to time, and let's assume that the change in momentum is equal to some final momentum minus some initial momentum, and this change took place during a time delta t, okay? Now, if F is 0, so no external force, okay, then we can immediately infer that PF, the final momentum, is equal to the initial momentum, okay? So momentum is conserved when no external force is present. And there is one more thing I want to say. It's not in my notes, but it helps with intuition. So conservation of momentum usually implies that, again, we have an object moving, let's call it m1, and it has some initial velocity, let's call it u1, okay? And it collides with an object m2, with mass m2, and no initial velocity, so a stationary object, okay? So in this scenario, okay, so this is before, this is situation before, and this is situation after, okay? So after, we don't care what's gonna happen, okay? So in this case, momentum is conserved, right? Because there is no external force when these two blocks hit each other. But some of you will protest that there is a force, right? There is a force. So at the moment of collision, okay, let me show you this. I hope it helps with intuition and comprehension. Let me know what you think about this in the comments. So at the moment of collision, okay, this is my M1 block and this is my M2 block, okay? We do have forces, right? So M1 hits the object M2, so maybe there is a force from M1 on M2 in this direction, F. But at the same time, there is a force in the opposite direction from mass M2, right? Which is equal and opposite in direction. And this is Newton's third law, okay? So the total force is 0 simply because F minus F is 0. But there is a presence of a force, okay? So sometimes some students get confused about this. So you don't have to know this. I mean, you don't have to think about this when solving problems, but it helps with intuition, okay? I mean, this is what's happening. So when we say no external force, we mean that when this collision happens, the two objects are let to hit each other by themselves, okay? If I put my finger on M2, the moment of the collision, then I do provide an external force. Therefore, the system is not closed anymore, and there is no conservation of momentum if I put my finger, okay? Because my finger represents an external force, okay? I hope this helps. So let's talk about common cases of conservation of momentum. So, okay, cases. So we will break the screen into before and after. Okay, before and after. So maybe we have a mass M1 with velocity U1 and a mass M2 with velocity U2. Okay, so the velocity of the second object is not 0. Okay, so we have U1 here and U2 here. And obviously for a collision to happen, U1 has to be larger than U2, okay? So the momentum before is M1 U1 plus M2 U2. So this must be equal to the situation after. So let's say that the two blocks move together, okay? So we have M1 and M2, and they move with some common velocity V. Maybe they collide and stick together, okay? So the final momentum is M1 plus M2 times V, and these two momenta are equal to each other, okay? Now, so this is case 1. Let's talk about the case, case 2, which is the case of an explosion, okay? So we have something that explodes somehow, okay? We don't care how, but the mass before is m and the velocity is 0 because it's stationary, okay? So the momentum before, what's the momentum before? 0, right? M times 0 is 0. But after the explosion, okay, so this is again to the right of this dashed line is the situation after. So maybe it breaks into two objects, okay? We have M1 moving to the left with velocity v1, and we have M2, the second chunk, that moves with velocity v2. So the object explodes, and it explodes into two pieces only, and they move in opposite directions, okay? So now the momentum before has to be equal to the momentum after. So the momentum after is what? It's minus m1 v1. Why do we use the minus sign? Because m1 moves to the left, okay? And remember that momentum is a vector quantity. And then plus m2 v2, okay? And also, in this case, also m is m1 plus m2, okay? So this is the second common case. Another common case, which is also kind of identical to the situation we just talked about, is a man or a woman on a boat, okay? So maybe we have some pond, and we have a small boat, okay, and a human. That's how I write humans for fun. So we have a human in the boat, okay? So the human has, the human has a mass m1, and the boat has a mass m2, and the system is stationary, okay? So the momentum before is 0. And now maybe the human, I will need to make some space. Maybe the human jumps off the boat and onto, I don't know, the pier or something. So the human jumps off the boat. So this is my human jumping, okay? So it has a momentum, he or she has a momentum p1, right? And as he jumps off the boat, okay? Then the boat has to move in the opposite direction with momentum p2, okay? So in this case, we have 0 momentum before, and this must equal minus p2 plus p1, okay? So these are the common cases for linear momentum, okay? And to close off this video, I think, yeah, this is it for collisions and momenta and such. We're gonna reintroduce Newton's third law, okay? So let's talk again about Newton's third law, okay? So Newton's third law says that when two objects, and this is the most important thing about Newton's third law, Newton's third law has to involve two objects, okay? Because questions are asked in tests and they try to throw you off. And do I have anything in my notes? No, but I will talk to you about some common examples where Newton's third law does not apply. Let me check my notes really quick. Okay. No, I don't have it for some reason. I don't know why. Anyway, yeah, I don't have an example here in my notes, but let's go back to this. So when two objects interact, okay, they exert equal and opposite forces, on each other. Okay, so let's talk about common examples. So maybe you have the Earth, okay, so Earth, and an object, I don't know what happened. Okay, so we have Earth and an object falling towards Earth, okay? So the object experiences a force, F, which is okay, we know it's the weight. And at the same time, the object actually attracts the Earth up with the same force, okay? And in the opposite direction, okay? So note that here we have two objects, okay? So Newton's third law applies here. You don't learn about this at the AES level, but if we have a positive charge and a negative charge, okay, then the positive charge is attracted by the negative charge to the right. But at the same time, the negative charge is attracted to the left by the positive charge plus, okay? And again, here, note that we have two objects. So, and I'm gonna mention a common example in which Newton's third law does not apply, okay, and they ask you to throw you off. So let's say I have a box sitting on the floor, and I have the reaction force from the floor and its weight pointing down. And they ask you, okay, the weight and the reaction force are equal and opposite to each other, right? Is this an example of Newton's third law? The answer is no, right? Because both forces are exerted on one object, okay? For Newton's third law, you need two objects. So I'm gonna write it here, not an example, of Newton's third law because both forces are exerted on the same object. Okay, so this example is not an example of Newton's third law. Okay, and I already talked about this. We already talked about this. Let's write it down again so you have it. So frictionless collision. So let's say that two objects move towards each other. Okay, let's call this object A and object B. Okay, at the moment of collision, so before and this is the after situation. Okay, at the moment of collision, I guess this is the floor and it's frictionless. Okay, at the moment of collision, this is A and this is B. Okay, I guess they have to be touching each other. So let me drag this. Okay, there, it looks good. So at the moment of collision, A exerts a force to the right, and B exerts a force to the left. Okay, so FA is equal to FB. Therefore, total force is 0. That's why the momentum is conserved. And this is an example of Newton's third law because it involves two objects. Okay, so two objects, two forces, one on one object, one on the other object, equal and opposite forces. Okay, so that's another example of Newton's third law. And to close off this video, we're gonna write this down again. So note, no external forces act on collisions. So yes, okay. I mean, if friction is involved, for example, or touching one of the objects or something like that, then P is not conserved. Okay, and this was the video about momentum and Newton's third law. Again, I think this is useful to international AES level students who take Unit 1, okay? And also to students from the UK who take Paper 1 probably, okay? And maybe it's useful in other aspects and for other high school students. So let me know what you think about the video in the comments. The next videos to come will be probably past papers because I have some old notes I can use. And we need to finish up Unit 1. So we have to still talk about materials and such. So expect more videos to come soon. Hope you enjoyed these videos. Please like and subscribe because the channel is really small still. And I would like to see it growing. So yeah, okay, this is it. See you in the next video. Bye.